So in the spirit of identities, we do have some identities using sum and difference of angles. So we went over some identities last time. And now in 5.2, we have these sum and difference identities for sine, cosine, and theta, and tangent. So what we're doing here is we're essentially taking two angles, we're adding them together or subtracting them, and now we're going to be able to use the sine and cosine and tangent, in fact, all trig functions on those angles that we're looking at there. Okay, so these formulas will be provided on this test that's coming up. This next test, there's not a lot of turnaround. I think it's actually around the next day after the math contest, like the 28th. So these formulas will be provided, but you've got to know like when and where to use them and how to use them correctly. So I think we were just starting this section last time. And I'm going to give you these formulas without proof. Some of these, they actually prove them. And as we go further in mathematics, we do want to prove some of these identities or some things. You'll see things proved. I think I told you about that. But for now, we're going to sort of choose our places where we pick to prove these or not. If you want a good graphical proof of these sum and difference formulas, actually in the textbook or the ebook, in that section, they do go over a graphical proof to sort of show you how these actually put together. So I think last time we were looking at finding more exact values, right? So we were looking at finding the exact value of sine. So we'll start with one here. By breaking it into its difference. So we might not know the exact value of sine of pi over 12, but we have two angles that we do know the exact values of that we can create pi over 12. And we talked about that last time, that when you have pi over 3, which we know that's 60 degrees, and pi over 4, which is 45 degrees, that if you subtract those, we get this pi over 12, which is 15 degrees. So what we can do is, now that we see that you can use a difference of angles here, you can replace that pi over 12 by two famous angles. Get your cameras. Okay. So when we replace them by the two famous angles, we go up and we look at which formula we're going to use. This one is, of course, sine of a minus b, right? Because we're taking pi over 3 minus pi over 4. And then we just replace the formula by wherever we see a, we plug in pi over 3. And wherever we see b, we're going to plug in pi over 4. So let's go ahead and do that. So using this formula here, we have sine, cosine. So sine of the first times cosine of the second. And then we have minus cosine of the first angle and sine of the second. So now we have our mastery tests that we knew. So I need some help with these trig values. I'm going to get you guys involved. So you should be all over this, hopefully. All right, so sine of pi over 3. What's sine of pi over 3? Shout it out.
Square root of 3 over 2.
Yes, it is. Excellent. Cosine of pi over 4.
One over square root 2.
Excellent, thank you. All right, cosine of pi over 3. So sine of pi over 3 was root 3 over 2. Nice job, Grace. Cosine is going to be 1/2. And then finally, sine of pi over 4.
Another 1 over square root 2.
You got it. Thanks, Connor. Okay, so that's going to be our value. So notice we're looking at adding two angles in there, or subtracting in this case. And what we're going to get out is a ratio. So now we have an exact value for sine of pi over 12 or sine of 15 degrees, and we can sort of reduce that a little bit. So it's going to be the square root of 3 over 2 root 2 minus 1 over 2 root 2. So if we wanted to combine those together, we could say that this exact value, it's sort of ugly or pretty, depending on what your definition is. It has a lot of nice irrational numbers in there, right? So square root of 3 minus 1 over 2 root 2. All right, now we don't have to memorize that value, but if you're wondering, that would be the sine of pi over 12 exactly. So when you type out an answer in your calculator and get the sine of pi over 3, I'm sorry, pi over 12, and you type that answer in your calculator, those would be exact up to the amount of decimals that you have in your calculator. Okay. So that's one thing that we can use it for. All right. I know that that's not very exciting, but it does give us a utility for these formulas. Are there questions there? Okay. Well, let's look at something maybe a little bit more interesting. So example 2, when I was looking at your tests, I had to, for some of those, when we were graphing them, I had to sort of think about like, wow, did you have the right answer or not? So sometimes we can list cosine as a shift of sine, right? Those are equal. So in fact, when we compare cosine to sine of x plus pi over 2, what's happening to sine there? What kind of shift or stretch or compression is going on there? For sine.
It's a horizontal shift to the left by half a pi.
Exactly. Very good. So we have an inside change there. It's an inside change of pi over 2, and we're adding on it, so it's going to the left. So horizontal shifts, horizontal stretches and compressions, they're always sort of counterintuitive. Great. So we should be able to prove that cosine of x is just sine of x with a shift of pi over 2 units to the left. Well, which formula would we go ahead and use to prove that? Which one are we going to use up there?
The sine sum formula.
Yeah, the sine sum formula. That second one down there in the first column. Great. So since we have for this one a sine of the sum of angles, we're going to just employ this one. So let's go ahead and check it out. We're going to do sine of x plus pi over 2. So we start with our left-hand side. So maybe when you're proving an identity like this, you wouldn't know where to start. Cosine of x, that's pretty simple. That's about as simple as you can get it. But now, since we have formulas for sums of angles, we can actually use that to expand sine. So if we use that formula above, that's just going to be sine of the first angle x times cosine of the second angle pi over 2 plus cosine of the first angle x times sine of the second angle pi over 2. Okay. So what is cosine of pi over 2, Jacob?
Cosine of pi over 2?
Uh-huh.
That would be, come on, 2. Isn't like,
Well, he's thinking about that. Jay, what is sine of pi over 2?
1.
Okay, so sine of pi over 2 is 1, and cosine of pi over 2 was what?
the -1? No,
Be over there.
it'd be pi, or no, not pi. 90 degrees? No, I'm like so lost now.
Okay, so you're thinking of the angle,
Yeah.
which is good. So you're doing that tracking of the angle. So pi over 2 gives us 90 degrees, right?
Mhm.
But we're looking for a ratio. So when we're looking for cosine of pi over 2, one way to think about it, cosine is the distance left and right.
Mhm.
So if we're just above there, the distance left and right is 0, right?
Yep.
So cosine of pi
So
over
it's
2
just 0.
will be 0.
Okay.
Great. Okay. Very good. So we're looking for that ratio there. Excellent. So we know that this is going to be 0, and Jay's right. Sine, remember on the unit circle, gives us the up or down motion. So at pi over 2 radians or 90 degrees, we're up at the top. So that's going to be 1. So when we simplify this, lo and behold, if things are right in the universe, this thing goes away because it's 0 times anything is 0. And then we have 1 times cosine of A there, and it's proved. All right. Very good. So we can actually verify something like that. And I like to do this. I like to encourage students to be curious and play around. So let's plot those two functions here. Do you see my Desmos up there on the screen? Yeah, okay, thank you. So if I plot sine of x plus pi over 2, then I have that red graph. And then of course, g of x equals cosine. That looks a lot like cosine, right? And it is, they're exactly there. So this is a true identity for every x value you plug in, and they're defined everywhere. Cosine of x will be the same as sine of x with a shift pi over 2 units left. Okay. All right. Very good. Questions there? All right. All right.
I did notice that sort of, it looks like partway through solving that problem, you switched from using X to A.
Oh, yes, I did. Yes, I did. Thank you.
I think you must have picked that up from the formula.
I did. I did. Thank you for correcting me there. Let me fix that. I appreciate that. Oh, okay. I can undo that. Don't worry. All right. Yes. Thank you for saying that.
Yeah, I was just like, hey, wait.
Yeah, I sort of got carried away there, didn't I? All right. So yeah, so this is cosine of the first angle. So A is x, right?
Multiple times I have watched one of the explanation videos for a problem and then put the answer they had, which is the wrong answer,
Yeah.
in
Yep.
the box.
All right.
Even when I have the correct answer on a piece of paper.
Yeah, so you got to trust in yourself. So you're going to get to the point where you're actually, if they make mistakes in the video, that you're probably right. You'll get to that point. So trust in yourself.
It's not that they make mistakes in the video, it's that they have a slightly different problem in the video.
Sure.
And
got
I
it.
give the answer for their problem instead of
Yeah.
mine. Oops.
Yeah, so just use theirs as a guide and go with
Yeah, I
yours.
know. It's just yeah,
All
I
right.
know. I try to, but sometimes I'll be like, okay, now to put in the answer, and then I remember the one from the video instead.
Yeah. Thank you, Alora, for
Sorry.
telling me about that A. Okay, so now it should be correct. All right. Anything else on that one? Okay, let's go ahead and go on to example 3. I tried to put these up by the formula so we could use these. Okay, so we have a function here. Let's say that we wanted to graph this and we didn't have a calculator. Would we know anything about that function, really, if we didn't have a calculator and we wanted to graph that? I see products of sines and cosines there. Personally, I wouldn't really know what to do with that. However, this looks like the right-hand side of a formula for a sum or a difference of angles. So let's see if we can use that formula to rewrite it and we can tell more about this function. Okay, so when we look at this formula here, when we look at this difference of products of cosines and sines, which formula are we going to use up there? Do you know, Nicholas?
The cos A plus B.
Yeah, it looks a lot like that first one. Nice job, Nicholas. So now we have to look at the right-hand side. And it looks a lot like this. Great, great. That's exactly what we're going to do. Okay, so in this case, go ahead, Nicholas. What is A and what is B in this problem? for
A is 3x and B is
Yep.
2x.
You got it. So we're going to use that formula wherever we see A, I'm going to try to put in 3x and remember that. And whenever I see B, I'm going to try to remember to put in 2x there for B. So if we use that first one, we have that f of x is equal to cosine of A plus B. But our A is equal to 3x and our B is equal to 2x. So I'm going to plug that in. There we go. I think I got it right this time. So we have cosine of 5x. Okay. So this should be equivalent to cosine of 5x. So if I were asking you to plot this one, if you know what the correct graph for cosine looks like, what would be the only change there?
The period would get smaller.
That's right. And what would the new period be, Grace?
2 pi over 5.
Exactly. Great, great. So we have a 5 there, and a 5 is that inside change, right? So it's a multiplicative inside change. Usually if it's bigger than 1, it stretches things out. That would be vertically, but inside is counterintuitive. So that 5 in there actually compresses it by a factor of 5. It would speed the graph up. So instead of 2 pi's units to complete its period for a cosine, now we complete 5 cycles of that in 2 pi units. So great. So this is just going to look like cosine. We know a lot about it now, and we could plot this. So this can be cosine of x with the period of its natural period of 2 pi, but it's been compressed by a factor of 5. So we divide by that b value, that value there. So its period should be 2 pi over 5. Let's go ahead and plot that. So our first graph was cosine of 3x. No, cosine 2x minus sine of 3x cosine 2x. No, sine of 2x. There we go. And then our next graph that we said that was equivalent to was cosine of 5x. They're exactly on. And so if I switch this up just a little bit, so I'm going to go over here and maybe switch my axes up a little bit. Let's see, the y-axis. I really want the x-axis to be switched here. So maybe go to from negative 2 pi to 2 pi. And let's do it in steps of the period. So let's just do 2 pi over 5 for a period. And so now that we've reduced that, you can sort of see what's going on there. Yeah, we're going to get that cosine graph that starts at the top and completes a revolution in 2 pi units, but this one's been compressed horizontally, so it's going to complete the 1 period in 2 pi over 5 units. So we have 1, 2, 3, 4, 5 periods in the 2 pi units because it's been compressed horizontally. So again, graphing can help you out. It can bring it to life. For some of you visual learners, you can use Desmos or your graphing calculator in radian mode to help you out and visualize those things. Great job. Questions there? All right, okay. So last one for this section, at least. So a lot of times we're going to use these formulas to help us find trig ratios. So an example for, we're given that secant of A is square root of 5 with A in quadrant 1, remember that notation from earlier. And secant of B is square root of 10 with B in quadrant 1. We ultimately want to find secant of A minus B. But you know what? We don't have a formula for secant of A minus B. However, we do know that secant is related to another function by reciprocal identity, and I claim it's cosine. So I sort of broke this problem into two. I said, well, let's find cosine first of that difference, and then we can use that to find secant. So we want to start by finding this cosine of a minus b, and then from that we can find secant. So we're going to be using this formula, of course. So let's go ahead and write that down. So this is how we would tackle these problems. We'd identify the formula we want to use. Most of the time, what I do is just sort of write it down. And remember, I want you guys to be cognitive of when you're doing your homework. We're looking for a ratio here. So sometimes it's easy, since there's so much going on here, it's easy to get sort of lost in the weeds and not to know exactly what we're looking for. So whenever we're looking at like finding cosine or a trig function of an angle, we're always looking for a ratio out. So what we should get out is going to be a real number, okay? A ratio. So I copied down my formula, and I think that's right. Okay, so I have information on A. I have information on B. But I don't have the information that I need. So from seeing that secant of A is square root of 5, can I find cosine or sine of A from that information? What do we think, Ali? So we have secant of A is equal to square root of 5. Can we use that to find cosine or sine?
Well, wouldn't secant be 1 over cosine?
It sure is. It's a great job. So if secant is 1 over cosine, then the cosine of A would be one over root 5. Does that make sense? So for a secant is 1 over cosine, then our cosine is 1 over secant. And so that would be just 1 over root 5. All right, so we found cosine of A, that's great. So Ali, what about cosine of B? Do we have that too?
1 over square root of 10.
That's exactly right. Okay, great. So I'm getting things with your help to fill in here. All right, so I think I'm ready to fill in some stuff now. So I'm going to go ahead and say, all right, I know that cosine of A is 1 over root 5. I know that cosine of B is 1 over root 10, but I still need to find sine of A and sine of B. Does anybody have any idea how we would do that? I think we've been doing this before, but it might have been a while, where we had one trig function and we wanted to find all the rest of them.
Use the Pythagorean theorem.
Exactly, Cole. Nice job. So we can use the Pythagorean theorem. We can use that Pythagorean identity. If it's easier, we can draw a triangle and use the Pythagorean theorem. And I think that that's usually the easier scenario, but we could use either one of those. Great job, Cole. So, okay, now it's your turn. So I'm going to go ahead and draw a triangle here. So cosine of A is in quadrant 1. So I'm going to draw a triangle here. Okay, Cole, what are the sides of this triangle? If cosine of A is 1 over root 5, where does the 1 and where does the root 5 go?
So the 1 will be the adjacent side, and then root 5 is the hypotenuse.
Excellent, perfect. Okay, so now if I want to find the opposite side, I could just do 1 squared plus y squared, right? Is equal to square root of 5 squared. So we use that Pythagorean theorem, just like you said. So y squared is equal to, well, root 5 squared is just 5. 5 minus 1. And so y squared is equal to 4. and y would be equal to plus or minus 2, but since we're in quadrant 1, it's 2, right? Okay, great. So Cole, what would the sine of A be now? What would the sine of A answer be?
Be 2 over square root of 5.
There you go. You understood me. Okay, great. So we can use that ratio. It's going to be opposite over hypotenuse. Great. And so this is what we usually do, or what I advocate for doing. You can use like the Pythagorean identity as well. That's less visual, but that's okay. So it sort of depends on what you want to do here. So I'm just going to model what you did over here for cosine of B. So let me see. Now my hypotenuse is square root of 10. That's bigger. My adjacent is 1. Here's B. And then if I want to find my y, I'll just say 1 squared plus y squared is equal to root 10 squared. I'll say y squared is equal to 10 minus 1, which is 9. So it looks to me like y is equal to plus or minus 3. Since we're in quadrant 1, it's 3. So my sign for this one would be 3 over square root of 10. And then we're in good shape. We can solve it. So, well, I have to have the plus there. Okay, I have to fill in the formula. So when I multiply radicals together, I can actually multiply the numbers and then just put them under one radical. So I have 1 over square root of 50 plus 6 over square root of 50. Okay, so that's 7 over square root of 50. Is there anything like a perfect square I can take out of square root of 50? Does anybody see anything?
Um, 25 and 2.
25 and 2 work. Thanks, Sean. So yeah, so this is going to be 7 over 2 times 25, and 25 is a perfect square. So I can take out 5. So for cosine of A minus B, I'm going to have 7 over 5 root 2. That'd be my answer. Okay, so that's cosine of A minus B, but we wanted to find secant of A minus B. So could anybody tell me what secant of A minus B is? What about you, Sean? Can you finish her up?
Will it be just 5 square root of 2 over 7?
Right on the nose. Great job. So of course, you're right. Secant is just going to be the reciprocal of that because secant is 1 over cosine. So this is just going to be 5 root 2 over 7. It's just going to be that reciprocal. Okay, so we ultimately wanted to find secant there. We don't have formulas for secant. However, we know that secant is just 1 over cosine, so we use the sum identity for cosine there. All right, great job. That's pretty much going to wrap up that section, unless there are any other questions there. A few things to sort of observe: that the algebra is a little bit messy here. So again, if you need to get up to speed, now's the time to do it. Just get a little bit of extra help. I'm here for you. The Math Resource Center is here for you. We can help you out. Okay. All right. Okay. Well, if I don't see any questions, so I'm going to clear this mess out, and we'll go on to the next section. Okay. So, all right, let's take a break. Whew, stretch. We all still doing okay? All right. All right. So I'm going to go back into Canvas. And I think I have another sheet up here. Let me go into my modules again. I think this one is the 5.2 and 5.3 notes. Yeah, so those will be available for you. And I'll just click on this and bring it out. Okay. All right. So great, we've done the sum and the difference formulas there. Everybody see my Canvas, the sheet? Yeah, okay, thanks. So we've done the sum and difference formulas. That's what we were just looking at. In 5.3, we're going to be talking about, hey, what if we take an angle and double it and put it in there? So I'm going to try to find the trig functions of a double angle. And so we will derive some of these. They're pretty easy to derive actually from these ones up here. So we will derive at least sine there. That's what we're going to do here by using those sum and difference formulas. But notice here that sine of 2 times an angle has only one form. Cosine has 3 forms. So when you're looking at cosine of 2 times an angle, you have 3 choices and all of them are equivalent. It's due to that darn Pythagorean theorem because we know that we can replace like sine squared by 1 minus cosine squared, and we can get an extra formula there, or you can replace cosine squared by 1 minus sine squared and you get another formula there. Tangent only has one version too. And by the way, tangent is sine over cosine of 2 times a. So you could derive that one that way. We're going to be looking at deriving the formula for sine of 2a using the sum of sines. So this is what we're going to do. So we'll prove this one from something we have already talked about. So if I say, all right, sine of 2 times an angle is equal to, well, I know how to find sine of a sum of angles, but a is just, 2a is just a plus a, right? So what if I said, all right, well, I'm just going to do sine of a plus a. That's 2a. And I know how to find the formula for that. So let's just go up here. Move my screen up a little bit. I'm going to use that first formula there, right? So let's write it down while I have it here. So I'm going to just use that first formula. And for a and b, I'm just going to plug in a. So I'm going to have sine of a times cosine of a plus cosine of a times sine of a. So that's from that sum and difference formula up there. So some of these identities now, we can actually use these new formulas. All of these so far that we've looked at, these the two types that are on the screen, those will be listed for you in your next test and the final. Don't memorize them, but know how to use them. Okay. So we have 2 of the same thing. So when we add them up, what do we get?
Just 2 sine A, 2 cosine A.
Yeah, so 2 sine A, cosine A, right? So remember, multiplication's commutative, so we could switch those 2 around if you want to put them in a certain order. So sine A, cosine A plus sine A, cosine A, there's 2 of them, and that's exactly what we would get up here for our formula, right? So we've sort of derived the formula for sine of 2a. Interesting. Okay. So we can derive the other ones that way as well. So I'm going to take a look at a few problems that were like this, like we did in the last section. So the first one's going to be 15 here, number 15. So this says the tangent of theta. So the tangent of an angle is equal to 3, and theta is in quadrant 1. Find the following. So I'm looking at 15 specifically. I'm looking at finding sine of 2 theta. So that actually t should be theta. Maybe I use t for theta. So I went to find sine of 2 theta there. And so I want to use this formula. That's why I haven't erased it yet. That gives us a formula for sine of 2 theta. The reason why I want to do that is because the information I'm given is in terms of just 1 theta, right? But the information I want is in terms of 2 theta. So I have to change that sine of 2 theta into something in terms of just theta. Okay. Whoops. So let me sort of erase some stuff here. Boop. So the first step I'm going to do is I'm going to replace that sine of 2 theta by what it's equal to. So I go up to my formula sheet and I say, okay, yeah, so sine of 2 theta is equal to 2 sine theta cosine theta. Okay. So now I need to find sine of theta and cosine theta. I know that I have tangent of 3, so can't we just make a triangle again? I know that theta is in quadrant 1. So my triangle's out here somewhere. And if my tangent of theta is 3, or 3 over 1, what are the sides of my triangle, Caleb?
The opposite side is 3,
Yes, it is.
and that would make the adjacent side 1.
Excellent.
And then would the hypotenuse be square root of 2?
Almost. But that's exactly how you do it. So let's try it. So 1 squared plus 3 squared is equal to that hypotenuse squared. So we'd have 1 plus 9, that's 10, is equal to r squared. So what's the hypotenuse?
Square root of 10.
Got it. Nice job, Caleb. Thanks for your help. So plus or minus root 10, but since we're in quadrant 1, we're using plus again. Okay, so now we have the triangle to be able to fill in what sine and cosine are. All right, Caleb, I'm sticking with you. What is the sine of theta from that triangle?
3 over square root of 10.
Yes, sir. And what about the cosine?
1 over square root of 10.
Excellent. Very nice. Thank you. So now we can find the sine of a double angle by using those single angle formulas. And this one's not too algebraically rigorous, maybe. Let's see. So I have 2 or 2 over 1 times 3 times 1, that's 6 in the numerator. And square root of 10 times square root of 10, that's just 10, right? It looks like both those are even, so a factor of 2 comes out. It looks like it's 3/5. Great. So that sine of 2 theta is going to be 3/5. All right. Questions there? So we're using that triangle approach again. Of course, we could use identities. I still think the triangle approach is better because it not only engages you algebraically, but it engages you with images as well. So there's one other thing to be sort of concerned about with these problems. This is sort of like a double check. And it's going to be important in the next section that we go over, probably not today, but next week. Where is that angle 2A? So we want to sort of concern ourselves with these things, like where if A is an angle, if A is in quadrant 1 and B is in quadrant 1, where is A plus B? Where's that angle? If A is in quadrant 1 here, where is 2A? What quadrant are we in? So the way to sort of think about that would be, okay, so I know that theta is in quadrant 1. So we can think of this, if you want to, in terms of, well, that means theta is between 0 and pi over 2 radians, right? 0 and 90 degrees. So where is 2 theta? Between 1 and what?
Pi.
Yeah, 0 and pi. So we just multiply everything by 2, and that's between 0 and pi. So what quadrants could we be in there for 2 theta? What 2 quadrants could we be in? Okay, 1 or that's exactly what my last class did. They were like 1 or 2, and I'm like, all right. But then somebody's cat walked right across their screen. I'm like, I can't see your fingers, man. All right, yeah, you're right. So it's either in 1 or 2. Sorry, I think I'm mirrored actually. So quadrant 1 or 2. And so we have to figure out, which one we're in. So we're looking at sine. So we get a positive answer for sine of 2t or 2 theta. So where is sine positive, in quadrant 1 or 2? Quadrant 1, quadrant 1. Okay. What about quadrant 2? Oh, it's positive there too. All right, so that doesn't help us out, unfortunately. So sometimes we just can't figure it out without solving for that angle. And by the way, we don't have to solve for the angles here. Without solving for that angle, we probably wouldn't know where it is. So since sine is positive in both those quadrants, I don't know that we could figure it out that way, but that's usually the way we would do it. There is sort of a tip off here. And so what I'm going to use, I think I know where this angle actually is. So what I'm going to use is tangent. So tangent of theta was 3, okay? So tangent of theta was 3. What do we know about the ratio of tangent? We know it gets bigger and bigger and bigger. So do we know that it's bigger than some value of tangent of theta is 3? What value of tangent do we know? Like, that's easy. In that
1.
first quadrant. Yeah, exactly. So tangent of what is 1?
Pi over 4.
Pi over 4 or 45 degrees. So 3 is bigger than 1, right? So we know that since tangent sort of increases until it gets infinite, that angle is bigger than 45 degrees. So double that angle would be definitely in quadrant 2, right? So that's one way that I didn't think of that before I was thinking of this problem, so before class. But I think that this one you'll find out that theta is actually in quadrant 2, just because of that ratio. So 2 theta, I should say, is in quadrant 2. So really for this one, we couldn't really sort of figure it out just by that information. So we had to use something else maybe. Okay. So don't worry about that. You won't need to get that specific, but it's just something to sort of think about. Okay. All right. So my next one, I have secant of 2t. Secant of 2t. All right. So we have a problem again. Secant of 2t, we just don't know a formula for secant of 2t, but we have 3 different formulas for its reciprocal, right? So cosine of 2t has something just in terms of cosine of t. It has something just in terms of sine of t, and it has something in terms of cosine and sine. So we have a choice here. We have a choice. So I invite you to be slick about this. When we look at our information that's given, we're going to let cosecant of t be square root of 5. And we know that t is in quadrant 2. What trig function do we have all the information about? If we know that cosecant of t is square root of 5, what do we think, Jay? What function do we know about?
I don't know.
What was that? I'm sorry.
I don't know.
Okay, no problem. So cosecant of t, if cosecant of t is square root of 5, we would know it's reciprocal. So what's its reciprocal?
1 over root 5.
Yeah, and that would be which function? So the reciprocal of cosecant.
Cosine.
It'll be actually
Cosine. Yeah.
sine. Okay, great. So, we can make this triangle again and use the triangle approach, but here, if you're slick, you can avoid that. So cosecant being square root of 5, we know that sine is going to be its reciprocal. It's going to be that 1 over root 5. So you know what? I'm going to use that formula for cosine, since I have a choice, I'm going to use the one that only involves sine of t, okay? And so I have all the information I need there. So, I mean, you feel free to use any formula you want. You have a choice of 3, but if you sort of have some insight, then you won't have to do as much work, okay? So do y'all see why it shows the one with just sine of t there? Because the information I was given, I could just really pick off sine of t. Well, if I wanted cosine, I'd have to make the triangle. Okay. So now let's go ahead and plug in. So I'm going to have 1 over 1 minus 2. So how do I plug that in, Jay? What will I have for my denominator there when sine of t is 1 over root 5?
-1.
Let's see, -1. Not quite. So what we're going to do is we're going to take this ratio here and plug in for the sine squared of t. But we have to remember what sine squared of t means, right? So sine squared of t is just going to mean sine of t. We plug in sine of t, right? And then we square it. So what we can do is we can take that ratio from above and just plug it in for sine. Okay, so we can take that above and plug it in for sine. So we'll have 1 over square root of 5, that's squared. Okay, and so that's our ratio now. So we do want to simplify that. And so we're into maybe a little more messy algebra here. But let's just try to work that out. So that's going to equal 1 over 1 minus 2 times 1 squared is 1 and root 5 squared is 5, right? So 1 over 1 minus 2/5. But we need a common denominator there. So I will go ahead and multiply this by 5 over 5. By 5 over 5. And then that will give me 5 minus 2 over 5, which is 1 over 3/5, right? And then I'll just go ahead and take the reciprocal. So when I have a complex fraction, I just take the numerator 1 and I multiply by the reciprocal of the denominator, 5 over 3. And so that should be 5/3 for secant of 2t. Look good, everybody? Okay, are there questions? Let's see if we can figure out where 2t is then. So we were given that t was in quadrant 2. So t was somewhere between 0 and pi radians. So if I double that, 2t is double 0 to double pi. And I guess that I need to be careful here, because if I'm in quadrant 2, then my bound there, part of me, is pi over 2, right? It goes from 90 to 180 degrees. So if I double that, then I'm somewhere between pi and 2 pi. So I'm in quadrant 3 or 4 now, but where is secant positive? Quadrant 3 or 4? Or both, or neither? Well, it should, I hope it's not neither. Quadrant 4, Grace? Yeah, secant's going to be positive in quadrant 4 because it's 1 over cosine. And cosine is negative in quadrant 3. So we can tell here that our new angle is going to be in quadrant 4. Nice job. Okay, so in this case, we're in quadrant 4. So 2t is in quadrant 4, since cosine of 2t is positive. Because secant is just 1 over that. So that ratio is positive too. Positive as well. Okay. Questions there? All right. Okay. Let's try one together here. I think we're ready for one together. Yeah. Okay. So some of these we can actually be given a certain expression in a different form. So I want you guys to try to simplify this one. So I do have it a little bit incorrect in my equation here. I have 1 minus 2 times sine squared of 75 degrees. I'm looking at number 37 there. So I want you to simplify the following. I want you to try to find an answer for that. And we're looking at a ratio, right? Because we're looking at sine of an angle, sine squared of an angle. So when you're looking at this, the first thing you want to do is you want to create an identity that's going to give you an equivalent expression. So we should know that 1 minus 2 sine squared something is equal to another version. Then after that, I want you to try to use your mastery trig values to get that exact ratio. So I'll give you a couple minutes here to try to figure that out. So go ahead and work on that. And then in a few minutes, we'll type it in chat and we'll see what we all got. I want to make sure that we're all on the same page. Okay, so remember there's going to be 2 steps. So the first one's using identity. Once we use that identity with that angle, then we should have a famous value. Take a picture. So we should have a trig function of a famous value that we should knock out of the park because we've done that mastery test. It's good to review too. And we're even in degrees. So this wouldn't be maybe a point in the graph, but it would be a certain value there, a certain ratio. Right. A little more time there. So if you have it, do go ahead and type it in the chat, but don't send it, please, not yet. In about 2 minutes, I'll give you just a little more time. I want to make sure we all get it. So I'm looking for 12 answers here, 12 people. Or in fact, 13. Somebody's off camera. Or wait, yeah. So I need to look for 13. Okay. All right, so go ahead and type it into chat. And we're going to send it here in just a minute. So here we go. We got 3, 2, 1, send it. All right. Let's see. Got 1. 2. You got 2. 3. 4. Okay, getting there. 6. Okay. I feel like likes on my photo. Can't wait. I can't wait till I get at least 12. Usually it's less than that. 7. Okay. I'm getting more popular now. 8. 8. All right, now they're flooding in. 8. A few more of you. We want to see what you got there. We're still working on it. That's fine. All right. 9. There we go. Slowly but surely. 10, double digits. Only at 3 more. All right. Who's holding out? Okay, well, at least I got double digits. Let's check it out. All right, so, okay, we have a lot of cosine of 2 cosine squared pi over 12. All right, okay. All right, so it looks like we didn't get this one. That's okay. I want to make sure that we know what we're doing here. So when I look at this 1 minus 2 sine squared, 75 degrees, I'm going to move the screen up just a little bit. Let's see here. We're going to use an identity to turn that into something we know. All right. So when I look at my identities that are available, I see, hey, 1 minus 2 sine squared a, hey, that's exactly the same as cosine of 2 times that angle. So that's the identity I'm going to use to sort of shore this up. So I don't really know what to do with the 75 degrees, but maybe I can turn it into a double angle, and I know that more about that angle. Okay, so let's check this out. So this, whoa, too far. This is equal to 2, whoops, not 2, sorry. It's equal to cosine of 2 times that angle A. And the angle A is 75 degrees. So it's going to be cosine of 2 times my 75 degrees. Okay, what's 2 times 75 degrees?
150 degrees.
150 degrees. All right. Hey, that's getting to be more about a famous one, right? So we can go ahead and we can figure out where this is. We need a reference angle now. So we're over here in quadrant 2. What's the reference angle for that bad boy?
30.
30, it is. So this is a 30, 60, 90 triangle. So this is going to be equal to plus or minus the cosine of 30 degrees. So what's the cosine of 30 degrees, everybody?
Root 3 over 2.
Root 3 over 2. Excellent. Now the last thing, is it going to be positive or negative?
Negative.
Negative. Why is that?
It's in quadrant 2.
It's in quadrant 2. Yeah, all students take calculus, right? So sine is positive in quadrant 2, but cosine's negative. So this one's going to be plus square root of 3 over 2. Okay, so that was that 2-step problem that we had there. All right, so I wanted to make sure that everybody was on the same page there. It looks like we weren't, but does that make more sense now? I want to make sure that we have a good feeling going into the weekend. Okay, all right, great job today. See what you can do over the weekend, and if you have any questions, stick around. Otherwise, have a great weekend, and I'll see you next time.